So I know everybody is tired, so I've tried to make a friendly talk with a lot of pictures. And it's based on a work with Nicolas Bitta, who is there in the room. So before speaking about snakes and domino snakes, I will go back to the 60s and the work of Hao Wang. So for some reasons that have almost nothing to do with tiling theory, he defined a very simple model of tiles. He was interested in some fragment of logics. So this model is very simple. Your tiles are squares, and you just add some decoration on the squares by putting a color on each edge. And you put the tiles vertex to vertex, and you have a neighborhood rule, which is, like in a jigsaw puzzle, the color have to match, and that's it. So you cannot rotate the tiles, otherwise everything becomes trivial. Well, at least all the questions that we address in this talk are trivial. So you cannot rotate them. And given a tile set like this one, you are interested in the set of all possible tilings. So for symbolic dynamicists, you can see this set as a subshift of finite type on Z2, so your alphabet is just the tiles themselves, and you have these local rules that are nearest neighbor rules. So that's it. So, okay, let's start with this simple example. So if I give all of you infinitely many copies of each of these 4 tiles, eventually you will get this kind of pattern. And why does it give a tiling of the whole plane? It's because if you focus, for instance, on the pattern inside the yellow rectangle, you see that the 2 vertical edges were the same sequence of colors, and it's almost the same for the horizontal edges. The colors are the same up to a cyclic permutation. So it means that I can repeat this pattern regularly. There is a lattice behind. And okay, I'm convinced that there exists a tiling because I can describe it to you with this finite pattern that repeats infinitely many often. So in the 60s, we don't know about Penrose tilings, we don't know about substitutive tilings, we don't know about aperiodic monotiles, we don't know that there are aperiodic tile sets. And unfortunately, you have examples like this one, where it's possible to tile the whole plane, but you never find the periodic structure like in the previous example. So Wang was not aware of this, and he was interested in a decision problem, which is this one. You take as input a Wang tile set, and you wonder whether you can tile the plane or not. So it's just the question. And surprisingly, one of Wang's students managed to prove that this problem, called the domino problem, is undecidable. So you cannot algorithmically decide whether this tile set can tile or not. So it was a surprise, and we could try to understand why the infinite grid, why Z2 has this property, by looking at tiling on other groups than Z2. So you can generalize the definition of Wang tiles and Wang tile set. So take a group and fix a finite generating set, a finitely generating group that you take symmetric. And you can transpose the model of Wang tiles. Our squares become just S-gons. And okay, you can produce the same formalism. So on this example, for 2 generated groups, you have the same square as before, but you can use this tile to tile Z2 or F2 or any group with 2 generators. And okay, the same for 3 generators and inverses and so on. And what is a tiling now? I just put a tile on every group element, and what I ask is that if I have a tile on an element G, and if I move by a generator, then the color have to match. That's it. And as before, we look at the set of all possible tilings. And as before, you can think about this set as a subshift of finite type, where the alphabet is our tile set. And you have these finite local rules, just nearest neighbor rules. OK. So as before, we can define the domino problem again. So now your input, you fix a group and a finite generating set, and the input is a tile set, and you wonder, OK, is it possible to tile my group with these local rules? So first, it's a nice problem. It's a problem about the group itself, because you can prove that this problem does not depend, well, the decidability of the problem does not depend on the choice you made for the generating set. If it's decidable for one generating set, then it will be for all the generating set. And better than that, it's really a geometric property of the group. So having a decidable domino problem is a quasi-geometry invariant. So it's really a question about the group and its geometry. So many people have looked at this problem. There are many nice results. And there is a conjecture that has not been disproven yet. What we suspect is that the only group for which this problem is decidable are virtually free groups. So there are some reasons why we are convinced that this conjecture is true. So here you have some elements that gives you a proof that for virtually free groups, then the problem is decidable. The idea is that this domino problem can be expressed in monadic second-order logic. You know that virtually free groups can be characterized by having finite tree width. And the graphs with finite tree width are exactly graphs for which MSO logic is decidable. So putting all this together, you get a very high-level proof that our problem is decidable for virtually free groups. You could also make a proof by hand using a brute force algorithm just to detect whether you can tile your virtually free group. And so the difficult direction is the other one. If I give you a group that is not virtually free, can you prove this problem is undecidable? And OK, there are some clues. For instance, it's known that if you take a non-virtually free group, there are some large grids inside the group. Large finite grids, but arbitrarily large. But OK, it's not enough to conclude because OK, we don't know where are these grids, and even more problematic, we would like to be able to encode these grids inside a Wang tile set to get a reduction to the domino problem on Z2. OK, so the conclusion is that this problem is too difficult, too much undecidability. So, OK, let's move to snakes tilings. So tiling Z2 or group, OK, too difficult. So let's look at a variation that is much simpler. Instead of looking for a tiling of the whole group, OK, we just look for a path, a simple path inside Z2 or inside my group that I can tile respecting the local constraints. So here is an example with two tiles. So on Z2, you cannot, well, on any group, you cannot get a tiling of the whole group just because you don't know which tile you put here. No one fits. But you can tile, for example, this infinite path. Okay, and if I look more accurately to my tile set, I can give a representation of it with a finite graph. So tiles are my vertices, and I have edges labeled by the generators of the group. And so, for instance, I have this edge here from this tile to this one labeled by the horizontal generator because we have red. Same for the vertical one. And okay, my snake here is just an infinite path in my graph. So with this representation, you can forget about the tiles themselves and just, okay, I can put letters and I really have my configuration in my group. And what is important to notice, okay, so there are many snakes that I can produce with these examples. They are not that complicated because, okay, let's say I'm in Z2. When I've started a snake, I can continue it only going to the top right quadrant. So there are no curves, nor spirals, nor complicated stuff in the snake I can get with this example. And okay, I know that if there is an infinite snake with my tile set, there is an infinite path in the graph. But of course, the difficult thing to detect is whether an infinite path in the graph corresponds to an infinite snake, because it may happen that a path here does not correspond to a simple path in my graph, because by putting these generators together, I obtain a word that reduces to the identity. Okay, so maybe the next example illustrates this. So I have this graph. So I can put colors on my groups with two generators if they satisfy the constraints given here. So I can tile the free group, for instance, with this kind of, sorry, I can find a snake inside the free group with, for instance, this kind of tiling. But if you look at the same constraints on Z2, there is no infinite snake. You can be convinced just by trying all possibilities. And actually what happens, for instance, this one, you cannot continue it, because if you're here, okay, either you come back, but you cannot do it because then you have A minus 1, which is not a simple path. And the other possibility is to go up, but then there is a conflict because I've already put a color here, and I cannot put a different color. So here, actually, all the cycles that I can make with generators and inverse in this graph correspond to a word that reduces to the identity in Z2. So there is no infinite snake with this example in Z2. Okay, so let's have a look a little bit more formally to snakes. What are there? So we can decompose a snake, so a theoretical snake, into two components. You have a skeleton that is just the infinite simple path in your Keeley graph. And on this skeleton, you put the scales, which are the colors. So you want your path to be simple, so you ask for this skeleton to be injective. And you can move only by generator or inverse or generator. So you want the relative move to be here. And you want that the scale satisfies just the tiling rules, so the matching rules given by our graph. Okay, and there is also a remark in this model. So we ask that consecutive tiles in the skeleton are compatible, but we don't ask adjacent tiles in the graph to be compatible if they are not consecutive. So for instance, here I have an example on Z2, these 3 tiles. I can produce this snake that goes like this. Okay, this tile is a neighbor of this one, but they are not consecutive. Okay, here we are lucky the color match, but here, if I continue, I have these 2 tiles that are adjacent but not consecutive. The color does not match, but we don't care about it. It's really about tiling the path in the order given by the path. Okay. So now let's define a decision problem that we expect to be simpler than the domino problem. So here is a infinite snake problem. You fix a group, a generating set, and you wonder, and the tile set, and you wonder whether you can find an infinite snake given all these elements. So what is true is that if there exists a valid tiling of the whole group with my tile set, then there is an infinite snake and a lot of them. But of course, we don't know, well, if the tile set cannot tile the whole plane, we cannot say anything about the existence of an infinite snake. Yes?
Just to clarify, infinite snake means infinite path in the group or infinite collection of tiles? Because they recycle probably.
In the group, in the group. Yeah, in the group. A snake with a skeleton and scales. Okay, so this is our problem. And just a few remarks. Okay, it's equivalent to look for a B-infinite snake or a semi-infinite snake or snakes of arbitrary lengths. By compactness, you can prove that everything is equivalent. Okay, so it turns out that this problem has been investigated for Z2 with a standard generating set. And there is a proof of undecidability for Z2 that consists in successive reduction to the domino problem that is itself undecidable. So if we want to know more about the decidability status of this problem on other group generating sets, okay, we have a look at the possibility to generalize this proof, but unfortunately, the proof is very specific, and we could not generalize it to any other group. And moreover, something that looks bad, at least for group theorists, the choice for the generating set seems to be really crucial. For the domino problem, there is a result. So of course, you don't care about the generating set. So if you have a subgroup with undecidable domino problem, then undecidability transfers to the bigger group. Here, for infinite snake problem, if you have a subgroup for which you know our problem is undecidable, then you can deduce something on the bigger group, but it forces you to use the same generating set as for the subgroup, and of course you add other generators so that you get the whole group. So, okay, there is at least this restriction, and okay, so we know that for Z2 and the standard generators it's undecidable. For Z with a single generator it's decidable. So we cannot generalize the proof for Z2. So we tried to find a transformation on group, a tuple group generator into another, so that undecidability is preserved. So we called it snake embedding. So we look for a reduction. We would like to define some operation so that if there exists an infinite snake for GS, then, and only then, there exists an infinite snake for the transform stuff. So what we found out is using transducers. I just recall here on an example what is a transducer. So it's just a finite set automata with an input and output alphabet. And here we have strong restrictions on the transducer. So we ask it to be reversible, invertible. So we have the condition on the way it works. So we ask the function that takes a state and the letter of the input alphabet to be injected for every state. And well, reciprocally, we want a unique predecessor if you know the state and you know how you arrive to this state. So with this definition, we can define, okay, and how does it work? If you take a word on the input alphabet, you can compute its image just by following the path in the transducer. So you start in the initial state, and on my example, AB, AAB, I just get X, what is it, B, Y. Oh, sorry, my example, no, sorry, A, then a B gives, so I get, okay, this X, then 3 times a Y, and then a Y, and so on. And with these specific transducers, I can define what is a snake embedding. So you start from a group G together with S, and you want to compute the image of each group element to arrive in H. And to do so, you use a transducer as before. And your snake embedding sends every group element to its image of, the image of any word that represents G under the transducer. And you can verify, you can check that you have this condition. So two words have the same image if and only if they represent the same group elements. So not only the function is well defined on the group, but you know that you have to get to the same element. If you know that if the two images represent the same group element in H, then the two words also represent the same element in G. So here is an example. I start with Z2 and the generator AB that commute, and I would like to reach the Heisenberg group, for instance. And for genetic set for age, I choose the standard one, and G is just the commutator of X and Y. And what transducer do I choose? This one, which is very simple. Every time I read an A, I write a G, and every time I read a B, I write an X. And we can check that the condition 2 is satisfied, because if I have two words on Z2 that represent the same group element, then if I compute the image, I will get a word on G and X. And since G is in the center, the two images will also represent the same element in the Heisenberg group. And second, reciprocally, if two words have the same image, well, if the group elements represented by two words are the same, then necessarily I've started with the same group element, and this is because I have chosen my transducer so that if I have a loop in my transducer, then necessarily I have the same group element as an output on the transducer. Okay, so with this example, what do I get? I have exactly a snake embedding from Z2 to Heisenberg group.
I have a very stupid question.
Yeah.
Why do you call it a snake embedding if there is no snake in the
there is no snake, but it's made to work with snakes. Okay. So the answer is on the next slide. Yes, and if you want to compare it with some other operations that you know on groups, it's a very specific case of translation-like action, because multiplication to the right by phi of g is a translation-like action. And so to answer your question, why did we give this name? It's because it preserves undecidability of the infinite snake problem. If I can snake embed G into H, and if G has undecidable infinite snake problem, then so does H. And the proof just consists in explicitly constructing a tile set for H starting from a tile set with G, and we use a transducer to make it work well. So we get, for instance, that Heisenberg group with this generated set has undecidable infinite snake problem. Other consequences for Z2 and Z3 and in higher dimension, we get that the problem is undecidable and it does not depend on the generating set. And with a proof with arguments similar to the one used for the Heisenberg group, we can prove that if you have a nilpotent group, well, that is non-virtually Z, then you know that for some generating set, you have an undecidable infinite snake problem.
Are these propositions like corollaries of the main of step 2?
Yeah. So here the idea is so G is an element in the center, exactly like in the case of Heisenberg, and non-virtually Z is because, okay, it's decidable otherwise. Okay. So, okay. Okay, so this snake embedded was really made to work with our infinite snake problem, and okay, we didn't find other transformation that works well, and so as you see, it's a very restrictive operation, and okay, we get this one is nice because this result. We can get rid of the choice for the generating set, but here it's still restrictive because we are forced to have this element, this particular element in the generating set. Okay, so as a second part, I would like to focus on the skeletons of our snakes. So remember, the skeleton is just the infinite path in our group. On which I just put my tiles. So if we look at the set of all possible skeletons for a given group with a generating set, so we get this, we can define it like this. So what is it? It's just the set of all possible infinite worlds on the generators and inverses, such that if I look at the finite factors that appear, none of them reduces to the identity. So it's a subshift, and you can define this skeleton by excluding the word problem of the set of all possible paths in the group. Okay, so what can we do with this subshift? Okay, you can compute the subshift for simple examples. So for instance, for Z2 with standard generators, okay, the word problem is very easy, and you know that an infinite path is simple or is a skeleton, provided if you look at every finite world, it's non-balanced in A and B. So you can compute explicitly describe the skeleton here. And what is also interesting is to restrict the set of possible skeletons for our snakes. So if we look at only a a subset of snakes, so not necessarily a subshift, we just restrict to some possible skeletons. We can define a decision problem which depend on the choice for the skeleton you can make. So it's a Y infinite snake. And what is nice is that if you have chosen the set of possible skeletons so that the language is regular, so there is a finite state automaton that recognizes all possible words that appear in the skeleton, then the problem restricted to Y becomes decidable. And what can we do with this result? We can look at, for instance, geodesic skeletons. So we restrict now to the set of skeletons for which each finite word that appears in it is itself geodesic. And so for Z2, actually, it's very simple to say whether an infinite word is a geodesic skeleton or not. Once you have chosen to write a generator and another one, then you are done, because you cannot use, if I've chosen to go right first, then if I go left at some point, it won't be geodesic. So this is a geodesic path, this one also. So it's a regular language. It's just the union of all the possibilities among the four generator and inverses. So you get this kind of result. Our infinite snake problem becomes decidable, for instance, in Z2, if you restrict the snake to only take 2 or 3 possible directions among the four A minus 1 and B minus 1. And if you look at the problem restricted to the geodesic skeletons, it also becomes decidable for Z2. Another consequence, if I know that all finite geodesic paths in my kilograph forms a regular set, a regular language, then my infinite snake problem restricted to geodesic skeletons will become decidable. And there are groups for which we know that the set of geodesic paths is regular, for instance, abelian groups and hyperbolic groups. And what is nice with this result is that these times it does not depend on just choice for the generating set. So for both abelian and hyperbolic, you can take any generating set, then you will get a regular language and thus get decidability. Okay, so to go further, we have looked at other similar problems. So for instance, in the talk I've made the choice to talk about only infinite snakes, but you can define a similar problem for instance finite snakes, just loops in your group. We called it the Ouroboros problem. You can also ask whether there is a snake which starts from the identity and reaches some given element in the group. It's a reachability problem. So I haven't talked about these problems for now because actually everything works the same. Why? Because these three problems, infinite snake, Ouroboros, and reachability, three of them can be expressed in a monadic second order logic. And as a consequence, you know that they are decidable for virtually free groups independently from the choice of the generating set again. It's also particularly interesting to look at the skeleton subshift because if you forget about all this snake stuff, snake tiling, you get a one-dimensional subshift that is defined from your group and generating set. And the motivation here and the notation comes from the snake tilings, but this object has been actually known for a long time So this is an extract from Rufus Bowen notebook. It's accessible on a web page from the PIMS of Vancouver. And okay, I don't know if you can read anything, but okay, this object called V is actually exactly our skeleton subshift. Okay, it defines the set of infinite words on generator and inverses, so that okay, there is no cycle that appear. And okay, so it's an object that is in itself interesting, independently from our tiling equations, and there is a lot of to say about it. Okay, Nicolas made a poster. I guess it's always there in the library, maybe, so you can have a look at it. And things we have not been investigating more yet. Okay, so there is still the hope to characterize which group generator have a decidable infinite snake problem, or the same for the other problems, Ouroboros and reachability. And another interesting question. So we've tried to look at tilings of an infinite path. Okay, but maybe there are other relevant choices for the shape you want to tile. And as soon as you have some kind of regular stuff or automaticity stuff hidden behind, maybe it should be possible to get some decidability results. Okay, you can, for example, look for tilings of trees instead of just an infinite path, and so on. So, okay, I think, oh, it's okay. Yes, before, well, as a conclusion, I would like to show you a picture that I found when I was preparing the talk, just to convince you that all these questions are actually deeply connected to real-life phenomena. Okay, I found this picture. So you have a snake on a Coxeter group. So thanks for your attention.
So thank you, Nathalie. And so if you've got question, I come with the microphone. So who's got a question? Yes.
Are there any results about surface groups or non-virtually free hyperbolic groups?
Non-virtually free hyperbolic. Okay, so for the geodesic version, okay, we know it's decidable, but otherwise, I don't know. I have so.
The domino?
Oh, sorry. Which one? The domino? Which problem? Okay, so maybe I can go back.
Problem, yeah, but other problems too.
Okay. No, sorry. I went. Okay, where is it? Okay, so here. So this is for the geodesic infinite snake. For the domino problem, so when you look for tiling of the whole group, it's known to be undecidable for all hyperbolic groups. So it's a result by Laurent with that. And for the snake, I don't know. I don't know more.
Yeah. Question.
A short question. Maybe is it possible maybe to say something about the topology of the skeleton subshifts, for example, contrabendix and rank, or something like that, for some cases at least.
So, which property of the skeleton?
Just topology of this space as a subshift. So it's going to be a big topological space, and so maybe there are some isolated points, or I don't know.
It's a good question.
And does it depend on the choice of, I don't know, generating set?
So I don't know. Yeah, it's a good question.
Other question? So, yeah.
Okay, this is very stupid, but how do you make that X in LaTeX?
You just take a picture and put it. Sorry.
So, do you have examples of groups where the snake problem is decidable with depending on the generating set? You said
No, we don't know.
there might be some problems, but
Yes,
you don't know that there is actually a problem.
No, we don't know, but probably there are weird examples where you have decidability for one generic set and decidability for the other. But for now, we didn't get any example of that.
So we should thank Nathalie again.